All right. So we're picking up with example 11c. What's that? I'm frozen. Yeah, very good. Thank you. Sometimes I beat myself up, a lot about doing that. I typically do that a lot where the screen is frozen, and then I'm like, dang it, you idiot, just don't keep doing that. And I know I should just let it go, but can't. Anyway. Huh? Yeah, very good. That's why I brought that up, but thank you. Good. All right. So determine if, that was a long way to go for that little thing. Yeah, but anyway. Determine if the integral from 4 to infinity, improper, of 2 over x plus e to the x converges or diverges. Well, there's two ways to do it, as we mentioned. You can either find the antiderivative and evaluate it and see if it's a finite or an infinite number. But is that something right there, 2 over x plus e to the x? Are we going to be able to find its antiderivative? No, we're not going to be able to do it. So we're going to do two things here. First of all, because it's improper and we're going out to the right, we're going to be approaching infinity as we go to the right. We can use our intuition to see if it converges or diverges. Now, the first thing you want to do is check to see what the function, that is the integrand, is doing as it goes out to the right. So what happens to 2 over infinity plus e to the infinity? What's happening to the y values of your integrand? They are approaching 0, okay? So that means that the graph of whatever it looks like is approaching the x-axis, which is a horizontal asymptote. So now the question is, does it approach the x-axis fast enough to converge, or is it belonging to the 1 over x or smaller lazy family and not converge? What does your intuition tell you? Converge. Why? It's got e to the x in it, right? You got 2 over lazy old pathetic x, right? Which by himself, he's like, diverge. But then you got, I'm helping you out, plus values of e to the x. So he's like, I'm taking over here. Boom, we're going to the x-axis. He's like, okay. So yeah, you are correct in your intuition. This one does converge. But we now have to prove it, okay? And we can't just say x is lazy, e is not. That would be a great argument, okay? So in order to compare it correctly, we need to find a function now that is whatter than that one, bigger or smaller? Bigger. Good. If I can find a function that is bigger than that and show that it too converges, then because this one is smaller, it must also converge. So how are we going to come up with that function that we can prove without a doubt is bigger and converges? Here's the thing. The answer is already kind of there. What we're going to typically do is not really add, but more subtract. We're going to take something away, okay? So doubling the numerator is a good idea, but it doesn't really affect, we're not going to be able to integrate that, right, Noah? Yeah, if we put a 4 on the top, we're still stuck with, we can't prove that that one converges. So if we take something away, namely something from the denominator, what would I take away? You want to take away e to the x? That would leave us with 2 over x, which diverges. So that would not be the right choice. If I took away the x, right, pathetic lazy x that wasn't helping at all, let's see. If I then compare it with 2 over e to the x, what I'm trying to prove then is that that one is bigger than 2 over x plus e to the x, right? That's what I'm trying to show. Now, I don't have to prove it, but I want to make sure that inequality is true. Does it work? X is taking on values from 4 to infinity. So if you add something to the denominator, you are making the fraction wider, smaller. Good. So if you take that away, you now have something that's bigger, right? Okay, in other words, if you make the denominator smaller of a fraction, you're making the fraction itself bigger. So this is the correct thing. So if it's not there, then you're going to typically take something away. All right, so here's the inequality. We now have shown it. So what we really just need to do now is take the integral from 4 to infinity of 2 over e to the x dx, show that it converges, and then use the comparison argument. Yeah. Oh, yes, we would. Gosh, thank you so much. This is less than or equal to that for all x greater than or equal to what would we say? 4. Man, I'm glad you caught that, Skylar, because, yes, that's an important thing. Because it may not be true for all x, but over the interval that we're integrating, it will be. So that's an important ingredient as well. Okay. So to integrate this one, we'll bring the e to the x to the top, and it's e to the negative x. Now, this doesn't show up as a multiple choice, or it might, okay? the way it might show up as a multiple choice that I mentioned yesterday is it might be one of those like multiple choice. Roman numeral 1 might be this function. Roman numeral 2 might be this function. Roman numeral 3 might be this one. And it'll say which of the following functions converge or which of the following functions diverge. And then you'll have multiple choices, 1 and 2, 1 and 3, whatever. But if this is a free response question, it's all about notation. So remember, the improper integral has to come from a limit process. I haven't wrote the limit yet, have I? Which is okay at this point still. The antiderivative, 2 goes along for the ride. I have to have a correction of a -1, and the antiderivative e to the negative x is e to the negative x. If you want to first write the limit at this line, there's nothing wrong with that, okay? What that does is it saves you from initially writing the limit as b goes to infinity. Oh, yeah, now I messed that up because I'm trying to chew gum and walk at the same time. And I always choke on my gum when I do that. So if you ever see me chewing gum, I'm not moving. Okay? Yeah, I can't do 2 things at once. Thank you for catching that, too. All right, so what I was saying is you don't have to write it with the integral. As long as it comes from a limit process, which could be on this step, you're in good shape. All right, so let's go ahead and evaluate it now. The limit as b goes to infinity. I got a -2 out front, beefy bracket. E to the negative bth power. That's kind of fun to say. Minus e to the negative 4th power. And now we evaluate just the terms with the limit. And as is so often the case, what happens to e to the negative bth as b goes to infinity? It goes to 0. So I don't have room vertically, so I'll kind of go horizontally here. I'm not really a fan of that. So we get 0 there, so we get a negative times negative. It's positive 2e to the negative 4th. Now, you don't have to make a statement, and this is a finite number, okay? If it were like important that it was greater than or less than 0, we would say that, but that's a finite number, so you don't have to state that. So now all we have to say is, so the integral from 4 to infinity of 2 over x plus e to the x dx converges. And then you can either say as well, also, additionally, 2, I'll use 2, and then, again, you just can't hide your excitement at the end, right? So, again, those are the essential elements of a comparison test. The inequality with the domain specified, and then the integration of the one you're comparing it to, showing that it either diverges or converges, and then, therefore, the one that we started with has the same behavior as the one we compared it to, okay? Now, again, we stated that inequality, so we don't have to state it again. On part A, they gave it to us. We had to state it as part of our argument, okay? But if you state it yourself for the first time, that's it. All right, letter D. Let's try this one. We'll talk through this one together. Determine if the integral from 4 to infinity of 2 over x minus e to the negative x converges or diverges. All right, kind of the same thing, right? Looks very similar. Looks very similar. In fact, the only difference is now this is a minus and it's e to the negative x. What does your intuition tell you about that one? Converge or diverge? You think that? Yeah. Let's, like we did before, let's see what's actually happening to the y values of the function, right? In other words, take the limit as x goes to infinity of the function. I want to know what the y values are. If it's like x squared and the y values are going up to infinity, that diverges like crazy. But if you plug in an infinity in the bottom, you get e to the negative infinity, which is 0, and you get x minus 0, which is x. So this thing is growing effectively like 2 over x, yes? So it is going to 0, but if it's growing kind of like 2 over x, it's going there kind of lazily. So you would suspect that it diverges, right? Diverges. All right. So, and it does. It actually does. Okay. So that your intuition is spot on correct. Those of you who said diverge. Now we need to pick a function then for comparison that does what? That's bigger or smaller? Smaller. Good. If I can find one that's smaller and prove that it diverges, then because this one is bigger, it also diverges. So again, we're kind of staring at what we need. We just need to take something away. So we're going to compare that one probably to 2 over negative e to the negative x. That one goes to infinity, doesn't it? As x goes to infinity? Just e to the negative x. I need to find one that diverges. How about 2 over x? Does 2 over x by itself diverge? That's the divergent piece. Now, you do want to bring the 2 along, because if you got rid of the 2, sometimes you're making it smaller, okay, which in this case we do want to find one that's smaller, but let's just bring the 2 along. And then here's what we want to show. We want to show that that one is actually smaller now, so less than or equal to this. So by kind of setting up the inequality that we would like to show, we set it up and then we just have to make sure it's true. Otherwise, we've picked the wrong equation. Yeah, that should be true, right? Because notice this is a minus sign. So as we go from 4 to infinity, e to the negative 4th, e to the negative 5th, e to the negative 6th, those are positive numbers, aren't they? 1 over e to the 4th, 1 over e to the 5th. Those are positive numbers. If you subtract a positive number from the denominator, you're making the denominator smaller, right? Which effectively makes the fraction bigger. So yes, now we know for a fact that that inequality is true. It's a true inequality. And so now all we have to do is take the integral from 4 to infinity of 2 over x dx, which you could do it 2 ways here. You could say this is twice a p-series. This is twice the divergent p-series with p equals 1, which is less than or equal to 1, and that would be fine. It is still a p-series. We don't have to start at 1 for it to be a b-series, but if it does start at 1, then we know the sum is p minus 1, or 1 over p minus 1. So you could do the verbal argument, or you could just do it this way. The antiderivative is 2 natural log of the absolute value of x from 4 to b, and you take the limit as b goes to infinity. So, I don't know. It might be easier just to do this, or rather than talk about the p-series. Because it's not a p-series itself, it's 2 times a p-series. But again, divergent times constant or finite is divergent. So this becomes 2 times the natural log of b, which is positive, so I don't need the absolute values, minus the natural log of 4. And now if we evaluate it, what happens to the natural log function as we go out to the right forever and ever? What happens to the y values? They get bigger and bigger and approach infinity. So infinity minus natural log of 4, which is a number, is infinity, and infinity times 2 is infinity. And so we say, so the integral diverges. This one diverges. Okay, and now we could say, so the integral from 4 to infinity of 2 over x minus e to the negative x dx has the same behavior. Diverges as well. Exclamation point. All right, so again, you had a couple of ways to show that 2 over x diverged. I just went with the math instead of the English sentences. Okay, cool. So if you understand this comparison idea, it's going to serve you well when we get to chapter 9. Because in chapter 9, 9.1, we're going to spend a lot of time determining if series, not integrals, but series, which are sums of numbers, if the sums converge or diverge. A lot of time spent on sums converging or diverging. And this comparison test is going to be very, very similar to a p-series instead of a p-integral comparison test. There are actually 8 tests that we're going to learn to determine if something converges or diverges later on. This is going to end up being one of the 8 tests. That means we have 7 more to learn in chapter 9. So if you understand this now, it's just 1 less to learn in chapter 9. All right, so good so far. Any questions on any of these? Example 11. Yes? Oh, dang it. I missed that, didn't I? I missed that. Yeah. I missed it. Yeah, you got to do it for everyone. Because this inequality may not be true for like negative values, right? So this inequality holds, dang it, for all x greater than or equal to 4. So you always use the value of x you're starting at. Thank you, Devin, for catching that. Sometimes I get so excited I just forget to do things, right? Right. I was going to say something that was inappropriate, but I caught myself. A rare time I caught myself in my head. Now you know. Now you want to know what it was, right? Okay. Yeah. Okay. Sometimes I get so excited I just forget to do things. Like I go to the bathroom and then I pee my pants. I'm just like, right? It's like, oh my God, oh shoot. All right, man, I'm just so excited. Okay. Anyway, there it is. I said it. It's on the recording. All right. So, whoa, look at that. Yeah. Okay. This guy is not blinking. He may want to, but he's not blinking. So this guy right here would be what I call the definition of vigilant. Okay? He's ever watchful. He is paying attention, right? Anyone know the movie from which this comes? Yeah, A Clockwork Orange. If you haven't seen that movie, it's a fantastic movie, okay? It's a disturbing, fantastic movie, as you could tell, right? It was like, oh, it looks like a Disney film, right? Yeah. Okay. When an integral is improper, when an improper integral has a vertical asymptote, either on the interval of integration or as an endpoint, one of the endpoints of the interval, then you need to be vigilant because it's going to be improper, but it's not going to be as easy to spot, right? For instance, if I ask you, gosh dang it, if I ask you to find the integral from 0 to 1 of, I'll rewrite that, 1 over the cube root of x, dx. You may walk up to him and be like, oh, from 0 to 1, how cute, right? Does that look like an improper integral from what we've seen so far? No, because they've been easy to spot up to now because we've seen infinity or negative infinity on one of the intervals. But this one is still improper. Why? Right. The domain of this function is going to be everything except 0. There is a vertical asymptote at x equals 0. And we're integrating from 0 to 1. So we have a vertical asymptote at the left interval of integration. All right, now let's see what that's going to, how is that going to affect it? Well, it's going to affect it kind of the same way going out to infinity approaching a horizontal asymptote is. You could think of this kind of coming backwards. Instead of going from 0 to 1, let's start at 1 and start going back towards 0. We're going to be approaching a vertical asymptote from the right-hand side. And now the question is, let me kind of draw something. Here's a graph. Here's 0. Let's say we're starting at 1. Let's say the graph just looks something like this. We have a vertical asymptote. So we're looking for this area here. We'll keep it as area because it's easier to talk about. As we approach then the vertical asymptote from the right, the question is, same thing. Do we approach the vertical asymptote fast enough to have a finite area, or does it go to the vertical asymptote kind of lazy and diverge? Because just like with a horizontal asymptote, you're going to have an infinitely large unbounded region. But can it go fast enough to have a finite area, or is it lazy and have an infinite area? So vertical asymptotes, again, are a little bit harder to spot. All right, so what would you think about this one? 1 over the cube root of x, also known as 1 over x to the 1/3. If it were a p-series, if we were going from 1 to infinity or 5 to infinity, would this one converge or diverge? It would diverge, right? Because the p is 1/3, it's less than 1. It goes to the x-axis pretty lazy. But now the question is, how does it go to the vertical asymptote at 0? If it goes to the horizontal axis lazily, does that mean it goes to the vertical asymptote just as lazily? Or does it save its energy for the vertical asymptote and now it goes, what did I say the other day? Forcefully? No. I don't know. Quickly? Let's see. We'll try it out on the calculator. We will try it out on the calculator. Does anyone want to, guess? Do you think it goes to the vertical asymptote lazy, just like it goes to the horizontal asymptote, and you think it diverges? Okay, thank you for guessing. We will see if you're wrong or right. I will put the function x to the negative 1/3 in y1, and now I'm going to go to the home screen and math 9 it. We, of course, are not going to plug in 0. I'm going to plug a number just to the right of 0, like 0.01. And then we'll go up to 1, and I'll just recall my function, alpha trace number 1. Syntax error. Gosh. Yep. See, I get excited and I forget to do something. Not that one this time. Okay, just the next. 1.430. Okay. So that's like really close to the vertical asymptote, and it's 1.430. Garel, you think it's going to infinity. So we've got a long ways to go to get to infinity. But you know what? 0.01 in the relative scheme of things is still a long ways away from x equals 0. So double II, if you look on your paper, double II is 0.001. So let's just move a little closer, right? Move a little closer. Okay, I hope the vertical asymptote doesn't mind us getting that close, right? Oh, 0.485. It did get bigger, and it should get bigger. We're moving closer to the vertical asymptote, so we're going up now, collecting more area above, and it got bigger. Gorel. You think it's going to infinity still? Okay. Does anyone else know? We only have 2 data points. That's not that many. So let's go to point I. That's like uncomfortably close, right? 0.0001. 0.0001. So if it is going to infinity, then at this point, being this close, we should see some serious gain in our area, right? Like it should be like 1 million. $1.4967. It did get bigger. In your defense, it did get bigger. It sure is. But is the writing on the wall? At this point, being a mathematical detective, does the numerical evidence still support your original claim that it approached 0? Would you like to modify that? I mean, that it approached infinity. Yeah, I would probably say, yeah, that it doesn't. Okay. What would you say then? Would you make a new guess based on anyone? Not just Gorel. Would anyone like to make a claim? You think it approaches 1.5? Sure. All right, let's see. Remember, we could break the calculator without getting punched in the face, Colin. I know you like to overload it with zeros, right? How about that one? Is that okay? Oh yeah. That's right there in the sweet spot. We haven't broken the calculator yet, but I don't think we need to break the calculator. I think in this case we can say it looks like it's what? Yeah, it is 1.4999999999. So what would you say this one is? 1.5. Yeah, and I think you're right. So that's kind of interesting. As a p-series going to infinity, it doesn't go to the x-axis fast enough. But it means, in this case, that it does go to the vertical asymptote fast enough. So it's kind of interesting. Look what we have here. Let's have a vertical asymptote and a horizontal asymptote. And let's say it goes to the x-axis kind of lazily, like this. Right? Now, here's what we could do with notability. Look what happens. As I make it go to the x-axis more lazily by taking the graph and tilting it, what is that doing on the left side as it approaches the vertical asymptote? Yeah, it's almost like piercing the y-axis. So you can kind of see the trade-off there. If it goes to the x-axis fast enough, look what's happening on the vertical. Now it's going to the vertical asymptote pretty lazily. But if I make it go to the x-axis pretty lazily, now it's going to the vertical asymptote more seriously. So because the curve is kind of locked into its curvature, it looks like there's a trade-off, yeah? Maybe it can go to 1 fast enough, but not the other. And if it does 1, it doesn't do the other. So at least we saw that with x to the 1/3. And now with notability, we can kind of see that maybe that's the trend that continues. So let us see if it does. All right. What about this one? The integral from 0 to 1. Come on, notability. No, come on, notability. Come on. Don't fail me now. Old faithful, come on. All right. 0 to 1, 1 over x cubed dx. If we were going from 1 to infinity, 1 over x cubed, the p-series would what? Converge or diverge? It would converge to 1 over 3 minus 1 if it went from 1 to infinity, right? But it's going from 0 to 1. 0 is another vertical asymptote. So based upon what we just saw, if it goes to the x-axis fast enough to converge, what would you say about going to the y-axis fast enough? It should diverge. We would suspect that this one diverges. You know, you can have one, but not both, right? You can converge on one axis, but not the other. Oh, okay. Let's see. Let's see if that's the way it goes. I will just come back here, and instead of like doing the motion of like moving closer and closer, I never want you to forget that it is a limit process. But seriously, we could just go straight to something that's really close, of x to the -3rd, and come on. Whoa! That's a 5 with how many zeros after it? 15. Is that a big or small number? That's a very big number. So that's evidence right there that it's approaching what? Infinity. Just with one calculation. Okay? So our suspicions are confirmed. This one is equal to infinity. This one diverges. If it's a convergent P-series, then it's going to be a divergent, we don't call them P-series anymore. We can call it a divergent vertical asymptote series, VA series. I don't know. There's no name. But once again now, there has to be a cutoff, doesn't there? Where's the cutoff then from going to the vertical asymptote fast enough and not fast enough? What? 1 over x squared? Well, let's see. Remember the integral from 1 to infinity of 1 over x to the 1.0001, that one would still what? Converge. So if we went from 0 to 1 of that, if everything holds true, that one should what? That one should still diverge. Haha, very good. 1 over x, poor 1 over x. He is the gatekeeper for both ways, okay? He's kind of the guy that determines who diverges and converges going to the right towards the x-axis, as well as going to the left towards the vertical asymptote at 0. This one, of course, diverges as you go out to the right, okay? We already know from 1 to infinity it diverges. What do you think it does from 0 to 1? It also diverges, yeah. Yeah, to be the gatekeeper, it has to be consistent. It diverges in both directions, all right? So we're going to call this later on, I think I mentioned it, right? When we talk about the series, 1 over x is important. We call it the harmonic series. Not the harmonica series, that's a line of harmonicas, okay? All right, so as you can see, if a function of the form 1 over x to the p's power tends to converge as we go to infinity, it'll tend to diverge as we approach 0 from the right at the vertical asymptote. The exception now, of course, is 1 over x, which diverges in both directions. Okay? And we'll do some calculations here in a second and prove that. Okay? Verify your results from example 12 by evaluating the proper integrals. All right, so now what you want to get in the habit of doing? When you walk up to a rock that's been there for a while, you want to get in the habit of like checking underneath it for rattlesnakes. You don't want to get bitten, right? Now when you walk up to a definite integral, you want to get in the habit of checking the domain because you don't want to get bitten if it's an improper integral. All right, so what's the domain of 1 over x to the 1/3? Well, x cannot equal 0. And because when you plug it in, you get non-zero over 0, there's a vertical asymptote at 0. All right, so is this an improper integral, even though it doesn't have infinity? Yeah, because we have a vertical asymptote. It could be at either the top or the bottom or somewhere on the interval between them. So again, a little harder to spot, so remember we want to stay ever vigilant. All right, good. So let's try it out. We're going to do something very similar to what we did with the infinity. Let's go ahead and go right to or cut to the chase. It has to come from a limit property. We don't have to rewrite the original integral with a limit. Okay? We can hold off on that. So let's go ahead and integrate it. This would be the power rule. Negative 1/3 plus 1 is 2/3. And instead of dividing by 2/3, we'll multiply by 3/2. But now, we don't want to integrate from 0 to 1. We want to integrate from b to 1. So again, this is where the limit can come in. This is the latest you can write the limit. And then you'd have the limit as b approaches what? 0. Now you have to be careful. We're approaching 0 from a specific side. Which side? From the right-hand side. We're going from 0 to 1. So if it's the left endpoint of the interval, we're approaching it from the right-hand side. So that has to be a one-sided limit. All right? If you wanted to rewrite the integral, because you're just kind of a thorough person, then here's what it would look like. The limit as b goes to 0 from the right of the integral from b to 1 of x to the negative 1/3. So you could still You can still do it up there. But if you want to integrate first and then put the limit, that's fine. It just has to come from a limiting process. All right, so we're going to evaluate the way we know how. 3/2, beefy bracket, 1 to the 2/3 minus b to the 2/3. And then the limit is still out front. So we're now evaluating the piece that has the value of b in it. So we're approaching from the right, but still never not first. For a limit, we use direct substitution. What do you get when you plug a 0 in for b? You get 0, right? Now, if you wanted to know, is it approaching 0 from the positive side of 0 or the negative side of 0, you could just plug in a value just greater than 0, like a positive number, right? A positive number squared is going to be a positive. So we're approaching 0 from the positive side, if you're interested. But we still are approaching 0. So this is 1 minus 0, which is 1, and we end up with 3/2. And of course, 3/2 is equal to what? 1.5. And what did we determine the integral was numerically up here? Yeah, we determined it was 1.5. We got really, really, really close. So the bunch of zeros and a 1, and it was 1.499999999. And so there you go. We verified it. All right, so let's verify this one. We said this one diverged. As we went to the vertical asymptote, it diverged. So let's go ahead and write that from 0 to 1 of x to the negative third dx. We'll integrate it. That's x to the negative second. Dividing by negative 2 is the same as multiplying by negative 1/2. Now we're evaluating it from b to 1. And out front, we have the limit as b approaches 0 from the right. So again, that's the latest the limit can come into the party. So now we got the limit as b goes to 0 from the right. Negative 1/2 is out front, beefy bracket. Plug in a 1, you get 1 to the negative 2th, which is 1, minus b to the negative 2th. All right, now we can evaluate it, and we got to be careful. If you plug in a 0, you get 0 to the negative second. 0 to any positive power is 0, but 0 to the negative second, yeah, that's really like 1 over b squared, which as we plug in 0 is infinity. And is it positive or negative infinity? That's important here. Well, yeah, when I just look at the b part, we're squaring it in 1, so it's positive infinity. So when I plug it in, and again, I don't want to do this because this is a free response, but of course it's 1 minus infinity. You don't want to write infinity there. That's kind of bad. So let's just realize that that goes to positive infinity, and then we'll kind of do that in our head. What would 1 minus infinity be? Negative infinity, right? Now here's where it changes. What's negative infinity times negative 1/2? Positive infinity. And there's your final answer. So this one diverges. So notice I said always to be careful with one-sided limits when the answer is infinity. Because if the answer was negative infinity, then it would be negative infinity that for the diverges instead of positive infinity. So you want to get the sign of infinity correct. It diverges to infinity. All right, so we just proved that. All right, so now we have a way to deal with improper integrals where we have vertical asymptotes. All right, now let's try some random examples without a calculator. 0 to 27. I don't like the dx up top. What are you doing out there? Get in the back. It's like when the dog comes in, you open the door and the dog runs. Get in, get back out. Get out of here. Get out of the numerator. Go. Stay, change, flip. Good boy. All right. Is this improper? It doesn't look improper. It looks very proper. Well, let's find the domain, right? We can't take square roots of negative numbers, but this is a cube root. But we can divide by 0. And what value of x gives us division by 0? 27. Is that come into play in this one? It does. I have 27 as an upper limit of integration, so this function has a vertical asymptote at x equals 27. Using your intuition, as we approach 27, the vertical asymptote, do you think we approach it fast enough to converge or diverge? Look at the function. Yes, converge. Because this function is basically a transformation of 1 over the cube root of x, which is 1 over x to the 1/3, which we have more experience saying, if we go from a to infinity, this is a lazy one. This one diverges as we go out to the right, And so the trade-off is then, as we approach the vertical asymptote, this would be approaching the horizontal asymptote, as we approach the vertical asymptote, it's going to do the opposite. So this one should converge. The exception, of course, of that flip behavior being 1 over x. It diverges both ways. And we can easily prove that by doing something like we did on 13. All right, so now that we know it converges, let's go ahead and figure out to what it converges. So 0 to 27, 27 minus x to the negative 1/3. Again, I'll save my limit for the integration line or the evaluation line. So my inside function is 27 minus x. What is its derivative? Negative 1. Do I have a negative 1 out front? Nope. Is that a problem, though? Nope. I just have a correction of a negative 1. All right. So now the rule of integration, blob to the negative 1/3 by the power rule is blob to the 2/3. And then I'll divide by 2/3 or multiply by 3/2. And then I'll put the blob in there. So now because 27 is the vertical asymptote, I'll take the limit as b goes to 27 from which side? From the left now. Good. Since it's the right endpoint, I have to approach it from the left, and then I'll evaluate it from 0 to b. Cool. Y'all are catching on quickly like I knew you would. So the limit as b goes to 27 from the left. We get negative 3/2 beefy bracket. We get 27 minus b to the 2/3 minus 27 to the 2/3. And now I evaluate the limit as b goes to 27 from the left of that term. Now notice the exponent is positive. That's kind of important. If it were negative, it would be 1 over, like we had in the previous problem. But this one's just to the 2/3, so never not first. 27 minus 27, 0. 0 to the positive 2/3 power is 0. If it were 0 to the negative 2/3, it would be some type of infinity. But it's 0. So we end up with negative 3/2 times negative. So this is going to end up being positive 3/2 times 27 to the 2/3. That's the cube root of 27 first, which is 3. And then 3 squared is 9. So this one ends up being 27/2. It converged, just like you suspected with your intuition. So rely on the P series to tell you if it converges or diverges going to a horizontal asymptote, and then just flip that behavior if you're going to a vertical asymptote. All right, let's see if we can get this one in before we take the stand and get the test. We still got time. dx, gosh dang it, dx. Intuition. Well, first of all, is it improper, yes or no? What's the domain? What's the only value that gives us 0 in the denominator? 1. So there's a VA at x equals 1. We're going from 0 to 3. So 1 is not one of the limits of integration. So this one should be good, right? Okay, yeah? Well, yes, we're there, actually. Oh, okay. Are we okay then? We're integrating from 0 to 3. Where does 1 live in relation to 0 to 3? Yeah, in between 0 and 3. So we are integrating through a vertical. Yeah, we have to split it up. Very good. Now, in this case, we do have to split it up at 1. So a little bit more work. The integral from 0 to 1 of x minus 1 to the 2/3, negative 2/3, sorry, dx. Remember, you need that dx there. If you didn't have that dx, then when you write the next integral, you can lose points. And then plus the integral from 1 to 3 of x minus 1 to the negative 2/3 dx. All right, so just for what it's worth, your intuition should tell you that this one what? Converges or diverges? The parent function is x to the 2/3, which going to a horizontal asymptote would what? Diverge. It's a lazy one, right? So going to a vertical asymptote, it should converge. Yeah. We're just going to be approaching the vertical asymptote from both sides, which is not a problem, right? You got a function that does that, and it either does that on the other side or it does that. But either way, it's approaching it fast enough from both sides so that it will converge on both sides. So we just have to split it up. Let's do this one MC style. I don't want to go ahead and write the limit. Are you okay with that? All right. It's a little bit more dangerous if it diverges, because then we need to know what type of infinity it is. So we really need one-sided limits. But if it converges, the negative exponent should become positive so we can evaluate it. So your inside function is x minus 1. What's its derivative? 1. Do we need a correction? No. So there's no correction. There's no rider. We go straight to the rule of integration. Negative 2/3 plus 1 is 1/3 times 3. And we evaluate it from 0 to 1. Well, okay, let's do it that way. I said let's do it multiple choice style, but you know what? That's cheating you. If we never learn to do it FR style, then we're going to lose points. So the limit as B approaches 1, this time we're approaching 1 from what side? From the left, and it'll be from 0 to B. I like it. Okay. Plus now we're going to get the same antiderivative, 3x minus 1 to the 1/3. But now we're going to go from, let's call it, I'll go C. Why not? C to 3, and now we're going to take the limit as we approach, as C approaches 1 from the right side. Yeah. Okay, so that would be the free response notation, and it's good to do it that way. All right, so here we go. The limit as B goes to 1 from the left. Direct sub, we get 3 beefy bracket, B minus 1 to the 1/3, minus 0 minus 1 to the 1/3. What's negative 1 to the 1/3? The cube root of negative 1 is negative 1. So notice there we have minus the negative 1. That's going to change the sign. So a lot of little places in here where we can make little careless mistakes. So be vigilant, but also be diligent. 3 integral. Plug in the top. 3 minus 1 is 2. So I get 2 to the 1/3 minus C minus 1 to the 1/3. And now we'll evaluate each limit, which in this case, never not first. If those were negative exponents again, we would have infinities, and we would have to know if it's plus infinity or minus infinity. But they're positive exponents. So when you plug in a 1, you get 0 to the 1/3, which is the cube root of 0, which is 0. So we end up with 3 times 1, and then plus, evaluating this one, never not first. We get 1 minus 1, that's 0 to the 1/3. That's the cube root of 0, which is still 0. So we get 3 times 2 to the 1/3. All right, so if it does converge and you didn't recognize it, that it's an improper integral, then if you don't write the limits and you just go for it, from 0 to 1, it should still work. All right, so in the end, we get 3 plus 3 cube root of 2. That's it. That's the answer. It is ugly. Now, what's interesting is it converges to that, but is that an actual number? Is that an actual area? Can you enclose a space with exactly that amount? It's got the cube root of 2, which is what type of number? Irrational. So this is kind of a weird one. It is a finite number for an infinitely unbounded region, so it converges to that number, but that number itself has no place on the number line, right? We know it's there by the well-ordering principle, but it has no specific place. So I always think it would be like the cruelest joke. If you're like an expert cabinet maker and you have like an apprentice cabinet maker on his first day, just hand him a board and say, hey, will you go cut this pi feet long for me? Give him a board that's like 4 feet long. Don't give him a 2-foot board and say, go cut it pi feet long. Give him like a 4-foot board and say, go cut this pi feet long for me. And as he walks away scratching his head, you're just kind of snickering, right? Good luck! All right. Would that guy be able to find pi on his tape measure? Probably not, no. He knows it's there. It's between 3 and 4. It's between 3.13 and 3.15. So he can get pretty close, but he's not going to be able to cut the board. So he brings it back here. I'm like, nope, go back. No, okay. I'm afraid to start because they might come interrupt us. Let's try it. You want to go for it? All right, we got 10 minutes, so if we have to take a stand and do the pledge, we'll just do that with all this in the background. Maybe I should just cut the speaker wire. Okay. And then we can always take a stand on our own, right? Yeah. What is the area? Ooh, positive alert. Of the region in the 4th quadrant. Okay, 4th quadrant. Bounded by the graphs of that, and, ooh, that. Okay. So step 1, let's graph it. 2 natural log of x. That looks like this, right? It just takes your parent function, natural log of x, and vertically stretches it by a factor of 2. It still passes through the point 1, 0. Excellent. So y equals 0, that is the x-axis, and x equals 0. And now it's in the fourth quadrant. So, ooh, it's this. Ah. All right, so how do you want to slice it, vertically or horizontally? Horizontally wouldn't be bad. You can actually do it horizontally. And you would be going from negative infinity to 0. That would make it an improper integral like what we've seen before, and you would do right minus left, and you could certainly solve 2 ln of x for x. So you could do that. I'm actually going to go ahead, because I want to work with vertical asymptotes. I'm going to slice it vertically, okay? So I'm going to go from 0 to 1. And maybe if we have time, we could do it horizontally as well. It just turns into a different type of improper integral. All right, so I got to do top minus bottom. So again, we abbreviate area, A-R-E-A. It's going to be the sum of the infinite slices from 0 to 1 of the top curve, which is 2 ln of x, minus the bottom curve. I'm sorry, let me back up. The top curve is what? 0. Yeah, my bad. Top curve minus the bottom curve is 2 ln of x dx. So that was kind of tricky. Top minus bottom. Huh? No, it doesn't. I'm slicing it vertically, so it's dx. We could do that. So you don't want the negative out there? You could do that. All right. So let me. Oh, sorry. To the flag of the United States of America, and to the republic for which it stands, one nation under God, indivisible, with liberty and justice for all. Honor the Texas flag. I pledge allegiance to the Texas state under God, one and indivisible. Please remain standing for the moment of silence. Thank you. This would make a great yearbook photo. Take a stand for calculus. We're all doing calculus. Stand up. Yeah. Okay. So I brought the -2 out front. Kept it as -2. From 0 to 1. 0 is the vertical asymptote. The antiderivative of the natural log of x.
If you are interested, please stop by and pick up an application. Students, a reminder, if you are in need of a VOE form for spring break, today is the last day to sign up for it. Anyone that signs up tomorrow will receive their VOE form on Monday the 19th. And today, during lunches in the Career Center, New Mexico Military Institute will be visiting if you're interested. And students, today's cafeteria raffle winner is 485-3802. That's 485-3802. And since we had an unclaimed ticket yesterday, we have another raffle winner as well. It is 485-3803. 485-3803. Please claim your prizes by sea lunch today. Thank you.
Okay, so the integral of natural log of x, it might be worth memorizing it. Okay, it shows up infrequently, but it does show up. So if you don't memorize the antiderivative of the natural log of x, you would have to find its antiderivative by doing integration by parts, okay? And because we only know then how to take the derivative of ln, you would let it equal u, and then dv would just be 1. So the derivative ln is 1 over x, the antiderivative 1 is x. This would be the backward Zorro method, but you could always do it tabular-wise. You take your first diagonal product, x ln of x, minus, and then you tie it off with the horizontal product minus the integral, bless you, of 1 over x times x, which becomes 1, which then integrates to give you x. So the natural log of x's antiderivative is x ln of x minus x, okay? It's just a little time saver if you memorize it. So anyway, there's how to do it if you don't. And it doesn't take too long because y'all are pretty proficient at everything you'll do. But let's go ahead now and at this point, because 0 is the vertical asymptote, I put a b there and we approach it from the right-hand side. So if I then evaluate it, we get b approaching 0 from the right, negative 2, b if you bracket, parentheses, 1 times ln of 1 minus 1, minus b ln of b minus b. Okay, so I need to evaluate this part here. Now, for what it's worth, what is 1 ln of 1 minus 1? What's the natural log of 1? 0. 0 minus 1? That's negative 1. So just to myself, I know that this is going to end up being negative 1. But I need to work on that. If I plug in, I get 0 times the natural log of 0 from the right. What is the natural log of 0 from the right? Negative infinity. What's 0 times infinity? Indeterminate. Ugh. Okay, so again, bench work off to the side. I got the limit as b goes to 0 from the right of b times natural log of b. You don't want to do it in there because it's way too much to write every time. So this is 0 times negative infinity, which is indeterminate. So L'Hopital's rule shows up a lot in improper integrals. We typically brought the b to the bottom, right? B to the negative first. And now when you plug in, you get infinity. And then 1 over 0 is also infinity. So you really get negative infinity over positive infinity. But it doesn't really matter. Still infinity over infinity. So now by L'Hopital's rule, I'll just say L'Hopit. We get the limit as b goes to 0 from the right of natural log of b is 1 over b, which is b to the negative first, all over negative b to the negative second. So now if I just clean that up, and I'm running out of vertical room here, I bring the b to the negative 2 to the top, and I get b squared. And if I add exponents, 2 plus negative 1 is 1. So this turns out to be negative b, yes? And now by direct substitution? Negative 0, right? Which is 0. Okay, sweet. So in this case, 0 times infinity was 0, 0, 1. Doesn't always happen that way. So if I did that work off to the side, that's okay. I can now import that number in. So this becomes negative 2 bracket. And remember, that was negative 1 minus this thing right here becomes 0 minus 0. Okay. So then we get what as our final answer? 2. So it turned out that that converged. Would you think so? Yeah. Remember, as we go out to the right, natural log, it's not approaching a horizontal asymptote. But as we go out to the right, it's going up how? About as lazy as you could be. I mean, it's the slowest growing function. So even though it's not approaching a horizontal asymptote, then as you approach the vertical asymptote on the other side, now it means business, right? And of course, if you were to do it the other way around, you would have negative infinity to 0, and it would turn into an e function, right? And we have more experience with that. E is going to approach the x-axis, going to infinity, muy rápido. So you would suspect that it converges, okay? We don't have time to do the thing horizontally, so we'll stop right there. It would be kind of interesting to do it. So we'll pick up with 16, and let me give you your test. Y'all didn't stop me in time, but don't leave without it.